Hey, thank you all for joining. In case if you don't know me, my name is Sundar Vedantham. I'm sitting right here in this corridor. I run a team that's developing firmware layer software called Event Machine for Nokia for the past few years. There are multiple team members of mine in this room. And there are many here who would know most of the material that I'm going to talk about. So you all can feel free to jump in and then contribute wherever you can. Casually, Muthu asked me if there is any document related to post-silicon bring-up. We've all been working on storage for a while, and then the device is coming in, it's going to be brought up. But how does the bringing up works, right? So that was his question. And I thought rather than just trying to find some document I can forward, I thought I'll give a talk, and if there is interest, whatever document I found, I can forward it to you all as well. This is Intel notice disclaimer. Since it's internal crowd, I can move forward. Before we actually dive into the actual silicon bring up, there is a lot of work that you all know that goes into developing the silicon itself. So in the topic wise, the actual bring up of the silicon comes towards the end. So I do want to talk a little bit about the pre-silicon verification. So many of you might be involved in different aspects of the chip development. So you may see your line appearing somewhere in this sequence that we need to follow. So in the pre-silicon verification, there is we'll talk about these three bullets inside briefly. Then we also need to talk about part screening that relates to parts yield and then binning of the parts. Many of you may have heard the terms, but we can talk about what each one of those things mean and what's the significance. Right? And then the board design and validation part where the storage device or any of the new silicon that we develop goes in. Then there are tools related to bring up and debug called JTAG and Ladderbach. We'll talk about that a little bit. And then the actual silicon bring up process itself with respect to storage, how is it being planned and what's going on. If you look around, search the web, there are material available, but I just picked this one diagram from the web that gives you the overall flow. I'm pretty sure we are all familiar with this since we work in this domain. So for a chip to be designed, first we go with the specification and then architecture, what kind of microarchitecture that it's going to take in. So since we are Intel, any of the cores that go in tend to be all like x86 based microarchitecture thing, but there are still subtle differences, for example, Atom core versus Xeon or something else. And with our LSI legacy, we have pushed out multiple silicon devices that had ARM CPU cores also, right? So we had ARM 9, 11, 53, 73, all that kind of stuff. Once the architecture of the device, not only core, but what are the blocks, how is it going to be done, etc., are all done, then we go into RTL design, the real-time logic design where you develop the chip design itself. Beyond that, there is physical design to figure out how the chip is going to be accommodated in the real estate that we have, what needs to go next to which other block to make work the most efficient, and so on. Once that is also done, then we go to the tape out. Tape out is the standard terminology in the industry, but within Intel, I have that in one more slide also. We also have this notion of tape in, right? Because we have huge SOCs that we are putting together for which different block IPs come from different teams, right? Then they all need to be stitched together into one SOC. So when we reach a point where we have all the individual IPs ready to be all connected together and made into one SOC, that point in Intel terminology is called tape in, right? So during our LSI days, for example, there was no tape in, there was only a tape out because the teams always work together to make one SOC and then move on to the next. There was no notion of individual teams owning one IP and then giving it to multiple SOCs at the same time. Even though the IP may get reused, usually the focus is on one device and then the next device. Right? So the tape out indicates something like where even the assembly is complete. So you have the complete the file that you can send it over. So when I explain it to my family and friends, I usually say it like, think of it as a book being printed. Right? So the tape out is a point where you have the draft ready. You've sent out a Microsoft Word document or a LaTeX file or whatever you have done to put the book together. So that's the tape out point. Right? You've finished writing it. You have the entire file that you can ship it off to the printers. And then the printer receives it and then makes copies of that printed, the physical manifestation, the chips actually get printed out. Again, there are a lot of companies in the world that are fabless, meaning they don't have a fabrication facility. In that case, the file goes to somebody like TSMC, right, which is Taiwan Semiconductor Manufacturing Corporation. So they receive the file and then they actually get the actual printing of the device done, right? Whereas Intel, of course, is the world's biggest manufacturer. So we actually ship it inside our company itself to the fab where it actually gets printed out, right? So when the printing is done, it's like the first book coming out. That is usually is the chip in-house back from fab point in time, right? And it's either at the same point or maybe right after that. We'll also often see a terminology called FCS, meaning first customer sample, meaning the sample is also being shipped out to the customer. Right? So that is the point. The chip in-house back from the fab is what the post-silicon bring-up is basically about. So in simple terms, you basically get the sample in the house, so you are going to put it into a board and power up the board, make sure all the components in the chip work, right? That's what it boils down to. But of course, you can write books on how it's done because there is a lot of detail to be gotten into. Then the testing, the manufacturing production test, as well as the validation of the device itself goes on from that point onwards. So we'll talk about what kind of testing needs to be done and what is its significance, etc. That is also post-silicon. But when we say bring up, we are more focused on putting the chip on a board and making the board do whatever we want the board to do, right? So that's our focus. So but there is also a parallel component that goes on where the factory does a lot of testing to figure out how the chip is functioning. And then there is also a notion of validation. We'll talk about that. When this is all done, then we are good for volume shipment, right? So we give it a SKU, put it on the Intel database, and customer can start ordering as many devices as they want. So many of you may be working on are like very familiar with pre-silicon verification. In the literature, when you look around, you will see these two terms being tossed around often. One is verification, other one is validation, right? So from an English dictionary point of view, they sound kind of similar. So what's the difference? At least in the industry viewpoint, when we say verification, we are really going down to the register level and then verifying that whatever the gates, the blocks, the system, the individual things as they are supposed to work as per the data sheet, they are doing what they are supposed to be doing, right? So that's verification. You're not really worried about how the customer is going to do or what's the whole chip is designed to do, etc. I mean, that's not verification. Verification is very low level. If I write this number in this register, is this pin turning on or off? Things of that nature, right? Really, really low level. Validation, on the other hand, doesn't worry too much about the individual register read and write. You usually use some software to bring it up and then verify that the overall blocks, the entire chip, is doing what it's supposed to do, right? And the validation can proceed in so many different ways. So, for example, if you take Snow Ridge, course, we know our main customers are Ericsson and Nokia. So, for example, Ericsson may want to set up 10,000 calls per minute. Nokia may want to pump so much of antenna traffic through the system, and so the traffic should come in through this interface. It should go through HQM. It should go to the core. It should come here. This you should be able to handle so much of bandwidth. All those kinds of things, right? So think of it from a system level. Then what the customer wants to do. What was the chip architected for? When you ensure that that is all working correctly and it's a good system device, that is validation. Right? So you can just keep that in your mind. So in the verification part itself, there is RTL simulation and verification. This is naturally really important because as the blocks get coded, you had RTL blocks for individual domains in the blocks of the chip. They get stitched together and then you make sure it's working okay. So there is a lot of verification that goes into in this particular phase, right? On the other hand, it's really slow, right? So it's really going to look at like clocks, look at individual bits, bytes. You trigger this one pin that's coming up, going down at that level, right? So you can imagine if you simply want to send one packet that needs to traverse through the whole device and come back, simulating the whole thing in RTL may take days, months, and maybe like booting an operating system may take years or something, right? So that's not the purpose of RTL verification. It's again at the low level, right? So if you really do this, if you raise this clock, is it responding on the other end? If you put this value in this register, is it configuring that device correctly at that kind of level? Is that adequate to like confirm that the chip is done and then ship it out? Absolutely not, right? Because you are like way too down into the individual register level and you are trying to do something and you are definitely going to miss a lot of higher level functionality. So that's where several other verifications come in. FPGA is one thing that we consistently use. So you might have heard about various systems we have. So for example, the FRIO systems that are there. FPGA is field programmable gate array. You may know that. Altera is one of the biggest FPGA company in the world that we have as part of Intel. So in this stage, what happens is there are these huge FPGA boards that have a bunch of FPGAs that are put in, right? And then you take the entire chip, like Snow Ridge, Lionfish, whatever, right? And you take the same RTL, I mean, literally individual clock, bit, byte, rise, fall, register, the entire design, right? You dump that, pour that into the FPGA, so you get a small section of the chip simulated here, right? FPGA, of course, is like general purpose, so you can design whatever you want, and because of that flexibility, it will also be inefficient, so it can't be as dense as a real ASIC solution or an SoC is, right? So in the real SoC, take any block, MAC or something, right? So you can just do the whole block in whatever, so many millimeter square area. FPGA may take one whole rack to emulate just that one block, right? So that's always called emulation. So you cannot even usually put the entire SoC, something like Snow Ridge, even in like one rack full of FPGAs, right? There is not enough space. You need like a lot more space to emulate one device. So usually you chop up the device into parts, then take whatever that you need to test, pour it down into an FPGA image. I mean, basically the teams generate the FPGA image. You put it onto the FRIO system, then that device mimics the real functionality of the ASIC at like gate level, clock level, every level, right? Still, it usually runs at like 1/66th of the clock speed of a real device, right? So it's really slow compared to a real device. So if a real device is running at whatever 1 gigahertz, this is going to run at like few megahertz or something like that. It's going to be like so slow. But you can do a lot more testing on an FPGA system compared to what you can do with RTL simulation verification. Right? RTL simulation verification, all you can do is write the bit, read, write. So it's really at that level. With that FPGA, you can really connect a traffic generator. You can send traffic in. You can go circulate, come back. You can load the software that you are designing for the device. You can do all that. But still, if you want to even mimic the entire device, you may need like a room full of FPGAs to mimic one device, right? You usually don't do that because it's cost prohibitive. It's extremely expensive. So we build maybe like whatever 7-8 FPGA systems, and usually there'll be discussions as to, okay, we are going to put these two racks together so that you can mimic at least like half the chip or something like that, and are individual racks that will mimic just one block at a time. And the interfaces to other blocks are all like understood, and we know what's supposed to happen. So you'll connect it, send traffic, see what happens, take it out. So functionally, it's a kind of a high fidelity simulation of what the chip will do, but at a very, very, very slow rate and in parts, right? So that's the FPGA simulation. Beyond that, there are also software simulators. They may not be exactly mapped to the silicon verification itself. It's sometimes the other way about. The silicon design is done. So what the documentation, what the data sheet, what the architecture manual says, that is replicated in software, right? So for example, for Snow-Ridge, we have a simulator called ASE, Advanced Simulation Environment. So this is basically just a program that runs on a Linux box, right? You can download it from our website, just launch it. So it's going to run on a Linux environment. So within that, you can instantiate a Snow-Ridge device. Right? We've been doing that for all our previous devices also. So maybe Lionfish, or before that AXM 5500, 5600, whatever you can think of. For everything, we had an ACE. The way this is constructed is this is not a faithful simulation or mimicking of the RTL logic at all, right? So in fact, one good example will be this. So few iterations back, we had one device that was ACP 3500 that had one DPI block. That's a deep packet inspection block, right? It was designed in silicon to pick up packets really fast and then use stored signature to see if that signature is found anywhere in the incoming packet, right? Basically think of virus scanning kind of thing. So that was done, and the major fantastic technology is the hardware can do it really, really fast, right? In the simulator, what we did was that same group that originally had created the hardware block, they had a simple C program. And the C program would read a text file that is stored in your home directory. And then you can, as a parameter, you can give some string, okay? So it's just going to search through that using a C program, right? Do a physical text string search in the file that we have provided. And if it finds it, it's going to say yes. If it doesn't find it, it's going to say no and stop. That was it, right? So you can think, I mean, we all can write some such C program that can do it right away, no big deal. But we took that program. So instead of just reading it once and then stopping immediately, team basically made it run in a loop, right? So pick it up, read, say yes or no, and then go back. So that way, instead of reading a file, you can apply it to a packet kind of thing, right, for each incoming packet. And then second, we changed it so that instead of reading a file from something stored on the hard drive, you can actually receive an incoming packet and then skip the header and then do the search and then provide the result, right? So that's step 2. And then step 3, there is like system C model that is used to construct the entire ACE simulator. So instead of just reading a file or something, we modified it so that it can like receive the input from the system C interface, run the code, and then give the result back in the system C interface, right? So we gave that to the ACE team. They just stitched it into the overall ACE framework, right? So this has got nothing to do with how the actual hardware will really do it, but it does the same functionality. You give it a string, you give it a series of packets, it can go and search for that particular string and tell you whether it's found or not. Right? What's the purpose of this? Once this is constructed, you can give this to customers months ahead of the actual silicon device coming out, right? And they can actually start developing applications. So they can really write code. I mean, I was talking about just the DPI one block, but the whole thing, right? So for SNR, that's what it's been done. So for HQM, there is a software implementation. For everything else, CPK, HLP, anything that you can think of, it's all been written as a model in C code and then tied together using the the system C interface, and then made into a actual simulator. So this is what ACE is. So you can, Ericsson or Nokia can just download ACE, instantiate a storage device. They can write application. They can generate traffic, send it in, receive it. Everything will work at a much faster rate. Still not at the silicon rate, right? But in RTL, you can't. In RTL verification, this is not possible to do, right? So in FPGA, kind of, but still FPGA verification is more to ensure that the chip design at the RTL level did not miss something. It's faithfully doing what it's supposed to be doing. Whereas the software simulator actually takes that input and then it goes around creating a simulator that customer can replicate as many times as they want in each PC they have. Each application developer can have a real application developed. They can run it, make sure it works correctly. And finally, when the actual device comes out, you can run the same application and it will automatically run. It's guaranteed to work that way, right? So it really left shifts the customer application development cycle.
We have all the registered rate file information to
Say that again.
in the ACE.
Yeah. Say that again. In
Rich file information and the full.
Yeah. So it's actually abstracted to the level that is needed to create an implementation that's useful to the customer, right? That's the purpose there. So we won't really, for example, you can think of the DPI thing. There may be a bunch of registers that are all configured to do XYZ in the actual silicon. Totally ignore that because that's not really needed, right? We just take what is the gist of that block is doing, and if a customer develops an application and if it runs here, can it faithfully run on the silicon? So we'll keep the focus, we'll keep asking that question repeatedly to develop the simulator. Now, Symix is another. It was originally, I think, started as a company bought by Intel, so now it's owned by Intel. In ACE, you can actually create multiple instances of one device, right? So you can create two storage devices and send traffic back and forth also. In Symix, you can do that, and you can even go further. So you can simulate an entire board or a rack. So a customer may be building a base station system that has multiple racks to 50 storage devices, all interconnected. That can be simulated in Symix, right? Sure. Yeah.
Is the software delivered by the IP developers or is it written by a customer team?
For the ACE simulator?
For example, if you're modeling CPK or HL.
Yes, yeah.
So does a team separately design it for the customer, or does the CPK team or HLP team is responsible for delivering?
There is the ACE team. For ACE, there is a team in Austin. For Symix, there is a team in Arizona, Chandler. So they just talk to the IP team. For example, in this DPI, that one we did, I don't know, 10 years back or something like that. In that case, we spoke to the Terari team, hey, how does it work? What's the interface? They said, oh yeah, we have this one little program. Maybe you can see this is how it works. Then we just took that. That's like a toy program, right? Then we amplified it to make it work. So if they have something ready that we can use, by all means. 99% of the time, IP block team won't have anything. And you can't imagine HQM team having a system C simulation written that we can immediately pick up, right? So the ACE team actually talks to them, reads the data sheet, understands the architecture, and then comes up with their own abstraction of what that block does. Same thing with CIMIX also. Why do we have two? Customers prefer one or the other, right? ACE is our LSI legacy thing. A lot of people are used to that, they like it, and then we use it. CIMIX, for example, some teams within Nokia itself, they like CIMIX, some other team, they are used to ACE. And since we have the team, so now the CIMIX team is writing their own implementation of HQM, their own implementation of CLP, HPK, whatever you can think of, right? They are putting together a thing. But whatever tests that we have done, or tests we have written to run on the ACE, they also run on CIMIX. And if it's not running, the teams go around figuring out, what's wrong with the design so they can make sure it's done. And then this model is delivered to customers so they can open it. Yeah.
Even in December there is some details about the efficiency the depth of the pipe.
Oh yeah, very good question. Yes, yeah, it does. But again, it is based on the analysis and understanding of the simulation team, right? So if the simulation team thinks this is totally useless with respect to a customer who's developing an application, they may choose not to put that information in there, right? But if it is useful, they can mimic that. So exactly, again, going back to that same DPI thing, when a packet comes in, it does a scan, and then when it sends out, it's actually a C code running on a whatever Xeon processor or something, right? But depending upon the packet size, what came in and how it actually processed it, it can hand compute in the code itself how many clock cycles it would take in the real CPU, in the real silicon, right? And it can provide that as statistics from the block, right? So similarly, if there is like HQM or NCAV3 something, if you want to look at Q depth, that kind of thing, if that's really important, that can be implemented. It can be modeled, right, inside the simulator. So people can actually see levels going up, down, and then you can check how much throughput you got through this interface, or how much crypto engine, how much did it really process. So you can get, it took so many milliseconds or so many microseconds, it maintained so much of throughput. You can get all those details, but that is all implemented by hand using C code. So we talked about tape-in. How are we doing on time? I'll keep talking. Tape-in, as we said, is the point in time when all the other IP block people have said they've understood what your interface is, how things should be, and they have delivered their IP, right? So the SOC team starts stitching it together to create the entire IP. That is tape-in. Tape-out, as I said, is the point where the book draft has been sent to the printer, right? So you are not making any more changes at this point. Then, as we said, the part when it is actually manufactured in the fab, then comes these screening process. So I'm sure you all heard enough about the 10 nanometer yield kind of thing, right? So basically, when the silicon wafer is created, you have those round wafers, and then individually each one of those rectangles represent the piece of silicon that's going to go into one chip, right? When we manufacture that, we really want, let's say, 95% of those rectangle blocks to be productive, useful thing that will go into chips, and we make 95% of chips, right? Only maybe 3-4% gets wasted. Currently, on the 10 nanometer process, our yield is really low, right? So people are really working to improve the yield so that the thing can be productive. So the design is good, the process works, you get some chips that seems to be working properly. You can put it, pack it, run it, everything runs great, but maybe a whole bunch of silicon that are cut they don't seem to be working properly, right? So that's a big problem because you are going to lose on the margin. So yield is
on the previous point, we talked about process and exit.
Yeah.
Is it being kind of limited?
at least in my mind, I see the FPGA as the emulation, right? Meaning the entire very faithful mimicking of the registers and interfaces, everything is emulated. So, I mean,
SLR also has a zero emulation model. So there is a thing that makes it
okay,
was having emulation model in zero.
okay,
And it's the RTL that is written in Intel
yeah,
is also written with if-that emulation switches.
okay,
So it works both for emulation. And they use this Unix scripts
okay,
to start the setup and run the actual emulation model.
okay.
We have a full emulation
Full
model.
emulation.
Would emulation be like that compared to FPGA?
Yes, I think so.
Yeah.
Yes.
Yeah.
I mean, even FPGA is one approach, and then there was what was the other one?
Palladium.
Palladium is another one, right? So it's like looks like washing machine size boxes. So then you can use that also. So there are different ways of doing this, right? So, but from a higher level, you have RTL where you are just doing register read write. Is this gate going up? That clock coming down? That kind of thing. Emulation where you are faithfully mimicking the device, but at a very slow speed and so forth. Then you have software simulator where it's got nothing to do with RTL, but it helps the customers get going with the application. So, so yield is really important. We are struggling with that, and it needs to go up for us to make profitable parts in the long run, right? So that's one. Then comes binning. Many of you may know. So even when this is all high-tech digital manufacturing, all the parts that get created are not necessarily equal, right, in characteristics. So when the parts are created, right, out of the fab, they are going to be tested in multiple ways. One thing that we do is characterize it so that to see, let's say, how much current it leaks, right? So how much, so that there is a lot of leakage current that's going to take up too much power to run the device. Whereas if it has like very little leakage current, meaning when it's not doing much, it's not leaking anything at all, fantastic. That's a good part, excellent part, right? So we separate them and put them on different bins. So there is bin 1, bin 2, bin 3. So really good quality, fantastic parts. Everything works perfectly, and then the no leakage current, okay, bin 1. Then some in the middle and not so well on the third one. Then the marketing and the sales team really works with the customers to see where each one of those bin parts can be sold, right? So if it's really, really high and fantastic, blah, blah, we may ask for a premium. So maybe the standard price may be the bin 2 one. So if somebody says, oh, I'm going to put whatever million parts and I really want like low leakage current, fantastic part, maybe they need to pay a little bit more because they are hard to come by, like high-end parts. The middle one, standard price. And then the low end, maybe there is a lot of leakage current, but maybe somebody is designing PCs and they're going to put one chip at a time. A lot of leakage current may end up costing you 2 more watts or something, and who cares, right? So they may just take those because we are willing to sell that at a discount, right? So they get binned that way. And then there are also other kind of testing that gets done. So EMI, EMC. So EMI is electromagnetic interference, and then EMC is for compatibility, right? So we really take the device, go put it in some special chambers, and then run EMI tests to see if there is some kind of radiation. Is the chip just totally collapsing, or is it running fine? Like what's happening, right? So we do those kinds of tests, and there is also thermal testing. So there are heat chambers. So you go put the device inside and get connections out. So you may be doing just making sure the cores are up, or maybe you may be sending 40 gig traffic and looping it back, right? these will be simple tests to be done not by major software engineers, but production technicians, right? So it's really simplified to something simple. You have a traffic generator that pumps in a lot of traffic and then comes back. Then you start heating the device up, right, to the temperature that it's certified to be working. Why are we doing that? I love this picture. So our devices go into base stations that are used all over the world, right? I think the left one was taken in like Sweden or something like that, and then the right one, maybe Arizona, something like that. So it really needs to work from like minus 40 degree centigrade to plus 55 degree centigrade, right? So that kind of extreme temperature. Sometimes you will see simply when you heat the chip up, when the part just expands a little bit, right? You will see connectivity issues that are not seen in room temperature. So we have horrible experiences in the years past where maybe the customer keeps saying, oh, something is not working reliably, but test all you want, same traffic, same test equipment, this, that, everything works fantastically. And then finally people figure out, oh, the temperature was incorrect. And then when you do, and the board bends or the part bends and connectivity goes away. And so again, there may be binning related to that, right? So, oh, this works very well in this temperature range, but here it has this problem. So maybe you will sell it to this kind of customer. Then comes the board design and validation itself. So here the point is we do need to validate the chip. That's the eventual function, right? But in order to do that, you need a circuit board. So you need to design a board. So when you design the board, there are different kinds of board designed by Intel itself. So the bring up board is the one that's usually much bigger in size, because we try to pull out as many signals, as many connections that are in the chip out, so that we have enough pins, TAP, test access points, right, to really dig into the device to see if something is working, not working. If something is not working, you have enough access to figure out why it's not working. Not only that, it will usually have sockets. So instead of taking the device and then soldering it completely onto the device, onto the board, at least the initial ones, we'll put a socket in there that has the exact number of pins that are ready to go. Then you can get the new part, just put it in, just press it hard and like lock it in place, right? Then you can use it just like any normal part. Works fine, you can test it. And once it's done, you can take that out and put another device if you want. Or maybe initially if something doesn't work, if you are suspicious that whether it's not the actual design, it's maybe just this particular part, this allows you to swap the part out and test it, right? Gives you some flexibility. But that's not valid for production, right? Because the socket costs money. There is always this BOM, bill of material cost, for anything that you want to manufacture, right? You really want to shrink it down to the bare minimum that's needed. So in production boards, usually there'll never be any socket. Instead of that, Intel itself does what are called reference boards. So these are functionally similar to what the customer would want to do, right? So take SNR. So it has so many blocks that we need to verify. So the main board, the Victoria Canyon that we are working on, a lot of connectivity, a lot of pins, a lot of interfaces where you can connect debug tools, utilities, and try to figure out if the chip is working properly. But you can imagine, why would Nokia or Ericsson would want to do? They want to do like this size board with like bare minimum stuff, and that's it, right? So we also do that kind of boards, and we give that to our customers. Why do we do that? Is to suggest good design guiding principles, right? So we may want to suggest maybe this memory should be close to this, or you should put this particular block on this side, or the airflow should be this way, in order to guide those things. Instead of them saying, do whatever you want, and then not working properly, we do these reference design and give it to them. So reference designs will usually come after the bring up part is all done. We know the chip is good, then we put it in reference design and give it to people. Often they use it for comparing, running tests, verifying that it's doing what it's supposed to do also. If it's supposed to carry 40 gig traffic, is it really doing it, right? Is it doing it without heating up too much? So they use those kinds of references. Then there are actual customer production boards. So there, the customer will really trim it down and make it as simple as possible. Plus, they may also have a lot of other requirements. So, for example, any Nokia board that they design, they want to plug it into multiple, they have this thing called air scale, air hub, those kinds of huge chassis that go into cell tower, right? So whatever they designed 5 years back, they want to be able to put the storage card into that so that they don't need to like throw away all the old equipment. So they want the card, the form factor, the interface, everything looking very similar so it can go into that. People who may not have worked on boards may not know this, so I just put this particular diagram in. I actually brought some of these for like show and tell, right? So you can probably like take these around. So this one is like a sample wafer kind of, not exactly a wafer, but at least you can see the square pieces that are there, right? So you can just send it around. And then in the actual devices, I believe this one is the Snowfish. Yeah. So this is like the previous Snowfish device, right? So the way the connections that are there, if you look at like, think of like our 555 IC or something like that, it will have just like 8 pins or something coming out, right? So these ones, they need to have a lot of connectivity. And so they have something like 2,000 connection points right here, right? You just circulate. Don't take away the chips, but you can try, and I usually keep some just to do like show and tell kind of thing. So the each one of the points that you see, it's called like a ball grid array. So there's like a matrix of the pins, right? So on the socket, you put it down like that and then lock it in place to get the connectivity. But in production boards, that will actually get soldered, right? Now the question is, it has so many pins. So in a flat surface, if you start pulling the connections out, you can do the periphery connections out, but you have a lot more pins inside, right? So how are you going to draw out all the pins to connect to all the components on the board, right? It's going to short circuit. It's not going to work. The way it's usually done is using multiple layers of the board, right? Modern boards usually have like 17, 20 layers. Right? So these are called vias. So this is the top of the board surface. So you have these are actual connections coming in. So you will have like a drilled hole that has conducting material that's poured into this. And then so this can connect this green line coming in to this layer, right? So this is like a through via. This one is called a blind via because it starts from the top. So it's actually getting cut off at the bottom. Yeah. So this connectivity comes here, but it's not going down all the way, right? So it's actually connecting to a second layer underneath. And then there are also vias being buried totally inside the board. So this is the top of the board. This is the bottom of the board. So this is the middle of the board where you have this hole in the cross section, right? So this is buried via, this is blind via, this is like a regular via that has through and through connection. So you can do really complex design using this. So you can pull out individual pins at different levels and then send it in different ways to get as many pins that you want connected, right? And then there'll be things like this surface mount, meaning all the components are right on the surface. Then there are these through holes, which are these, and there are silk screen, which means that the component that are all installed on the board, they're all written out or indicated. You might see like R33, like resistance 33 or something like that listed, right? And then you can do the entire thing on photo etching, and then you can like do individual planes and then like build them all together and like make it into one board, right? Still, when I say 17 layers, still the board thickness is only about this much. So it's made so thin. And finally, you have this ROHS, ROHS, that's reduction of hazardous material, something like that. So it's actually a standard. So you need to send the boards, for example, it should not contain any lead, right? Things like that. So you need to get ROHS certification. So any board that you design, if you're doing a reference board, maybe if you use lead, it works better, connectivity is better or something. So, but you can't give that as reference board to customer because they can't copy that design and use it, right? So you need to make sure it's ROHS compliant. This is a lionfish board, right? So in case if you're all not seeing that on a daily basis, so I just brought one that's like the inside of the lionfish board itself. So the actual part itself is sitting here. So you have a huge heat sink and a fan sitting on top of it, and all these fans, there is like linear flow, that the amount of air circulation that need to be maintained. So we do that. So this is the actual part itself. So this is one of the bring up board that we regularly use for lionfish testing day in and day out. This is what is in the lab, and call it the Waco board. During this silicon bring up, there are also these two things that you'll keep hearing all the time. One is JTAG, that's Joint Test Action Group. That's an industry standard established in the 90s. So they have defined a spec as to how silicon design should have testability, right? So what kind of access port should it have? What kind of interface should you provide? So when the board is up, you can actually connect the JTAG interface and control the device internally. So you can you can do things like boundary scan. That means, let's say you have HQM, you have CPK, something, then you want to verify that the interface is right? So you can use JTAG to do that kind of thing. So that is a standard. And then there is this company called Lauterbach. That's a German company. So they have one product called like Trace32, which we commonly use all the time. So that uses the JTAG interface to actually connect to a board and do whatever. Yeah. Yeah. Actually, there were like there are a lot of interesting websites. So Intel definitely supports like Lauterbach, Trace32 debugger, right? So you can look these things up, JTAG and like boundary scan, those kinds of things. There is also, this is that Trace32 Lauterbach thing. So you basically have the tool connected to your board, and that's pretty much how most of the debugging, trace analysis is all done for most of the embedded systems. Originally, these were designed or at least thought out to be used for board debug, but this is what people do for silicon debug most of the time now. So this one comes to the actual, the Intel SNR validation process itself, right? So to come to this point, you really need all that knowledge. So only then you understand like what goes on. So we really go around chopping the time up into week by week, right? So you can see FCS, that is the first customer sample, right? So that's the first device that's coming in. Then we break it down by week 1, week 2, week 3, week 4, etc. RTK refers to the real-time operating system software that will come from the Austin team. So on the first week, you can see JTAG interface mentioned right there, right? So the purpose is to initially just enable the 10G, 25G interface using JTAG interface, right? So the device comes in. So what do you do? There is also another PDF I want to show. So we do something like this. On the initial days, it's almost like hour by hour planning, right? So this SNR phase 0, it's optimistically 5 days, right? So that's what is being planned. So when the device comes in, physically some engineer is going to be responsible and take it and then put it on the actual device. I mean, on the board, right? It could be socketed, you put it on, connect, and then you just power it up. And of course, before that, the board design engineers would have checked the board itself without the device, right? So there are a lot of planning going on in like getting, okay, how many boards do we need without device? How many do we need with silicon and so forth? So in the without silicon, you can do a lot of things like, are the other components working okay? Is the power lines running properly, right? If I connect a JTAG here, am I seeing all the signals coming through? Usually there is an FPGA that's needed to like start the system or like manipulate something. Maybe there is an external host that's connected that will start talking to the device itself. Are all those systems working okay, right? So they're going to test and verify that. If that is all okay, so you can imagine a huge NAT chart, right? So all that work goes in parallel, software development, RTE development, all that. Then when on the day the device comes in, you should have the board ready, you should have the software ready. So for example, on the software side, for months, we've been planning to get what is like bring up ready RTE, right? So the RDK, the real-time development kit, previously used to call it RTE, real-time environment software. So the Linux, the U-boot, and the RTE software that should be ready in what we think is appropriate for actually bringing the device up, right? Of course, it may have bugs, it may need to be tweaked as time goes by, but what we think is ready. How do we know it's ready? That's what is tested with the FPGA, that's what tested with the ACE and simulator, all that. And so we think, yeah, we are there, kind of thing, right? So on day one, it gets put into the board. And once it's put in, there is a notion of keeping all the individual blocks in reset mode, right? So this is done either through some JTAG interface or some register write or any of those, right? So by that, you mean you are not letting anything run. So you're just clamping down everything and then holding it down. So the first step is to go through this process. So we have without NAC, right? So not even that network acceleration complex. So first boot the device. So we just want to see if the BIOS is coming up, things of that nature, right? If that's fine, then you start releasing the NAC out of reset. And once it's out of reset, each block is designed to do some XYZ, right? So if, for example, if you take a core, that's going to go to like register instruction 0 and then start executing whatever it's there right away, right? So similarly, NAC, maybe it will start bringing up the Ethernet interface and things like that. So then you actually go through, there are actual people that are assigned. The initial bring up is going to go on in Guadalajara, Mexico. So there is like phase 1, phase 2, phase 3, 4, 5 listed. So when you walk through these steps and when you have these items done, right? So it's Norwich with NAC out of reset, the boot script is running, and then the ATV, this Ramon blocks that's working, cores are fetching instruction from the SPI interface, etc. So when these are all done, we call it, okay, this phase 0 bring up is done, right? Of course, we haven't done a lot of other things that the board is supposed to do. And so then you move on to phase 2. In this one itself, there are 2 boards. So there is one board called SVP, that is the prototype board in which Norwich is going to be installed. But that is for like very, very basic initial bring up kind of thing. And then the actual bring up is a more detailed, elaborate bring up that we'll use for extensive subsequent development testing is this Victoria Canyon board, right? It's a bigger board, something like this. So then we go into phase 1. You're saying optimistically 7 days. So in this one, we define an entry point, meaning all this should have been completed. And then we are able to get additional blocks out of reset. We are able to maybe send 10 gig, 25 gig traffic and just do a loop back, right? So you just know, okay, send it in, it comes back. So that interface is up, it's working up to that level, right? So that is the entry point. That means unless you have these criteria met, you cannot start phase 1, right? But if these things are met, then you can move on. Maybe there is a different team associated with this, or maybe some of these team members overlap. So then the BIOS focus comes in, and then the OS focus comes in. So by the time you finish this phase 1, you should have the Linux prompt. That's a big hooray moment, right, for anyone. So so the VC catch up with SVP, meaning the Victoria Canyon and the SVP are at the same level, and then beyond that we can do a lot more with Victoria Canyon. Then the FIs are brought out, the channels are all working. Then you can actually like connect it to Ixia, traffic generator, things like that. Right? When that is done, then you go into phase 2. So you already have the N cores available. So you may have whatever 24 core, 34, 32 core, something, but all the cores are still not available, right? Maybe you'll have 4 cores available. But that allows you to do a lot of things. So you should have at least some cores available. So for example, in this, everything works, but the Tremont Atom cores are not coming out of reset. That means you're not done with phase 1 yet, right? So you're stuck. So you need to continue working on that. So the NAC is out of reset, firmware is loaded, NIC and switch mode is working, BIOS is working, port links are up, 10 gig, 25 gig, you are able to send traffic back and forth. Then we are good. Now we can really start loading RDK, you can start bringing up different blocks that are all needed. So we are loading the RDK drivers, right? So when this phase gets completed, you should have loaded NVM, all these interfaces working, CPK, HLP, CPM, Roman, all those done. Then we say Victoria Canyon, this board is sort of up and running. Still, it's not done, right? So you still have to go through additional phases where you may need to pull out all the other clusters out of reset, then get all the individual drivers working and start really like ramping up on the amount of traffic that it needs to go through. Then for this BTS is like base station something. Yeah, so this is the for Ericsson and Nokia, what are the main flows that they are going to expect, right? So maybe through the Ethernet interface, they want the traffic coming in, a lot of switching taking place, then it goes to HQM, then you should go to the core where there is some application running, you do XYZ and then bring it out, right? Maybe that's one flow. And then there's another flow from core, you want to send it to crypto, get some encryption, decryption going on, take it back, send it out, right? So that's another flow. So people have spent a lot of time and come up with like 5 different flows that are really critical for base station customers, Ericsson and Nokia. So the deliverable for this phase 3 is verifying that all 5 of those flows are working consistently. By the time we are done with that, then there is that exit, right? So when we are done, we can say, yeah, the board is up and running and we are all good. And beyond that point, my team, for example, we are doing what's called an event machine. So that runs on top of RDK and DPDK. That will set up paths between different cores. It will generate maybe some traffic in one core, send it through HQM to out through the Ethernet interface to a different device. And if you go all the way up to that other core in the second device, things like that, right? So we will step in and then start running all the code. So we have the code developed, the code tested. We have a bunch of tests that are running on a daily regression, all on the ACE simulator, right? Because we have that, we are like miles ahead, right? If we don't have those simulators, we can't do that on FPGA. We can't do that on RTL. We'll just be sitting around, right? So now we have all that already ready, prepared. So once this board comes to that, next day we are going to jump on and start running our tests.
What is the CE? CE start.
I think PO is power on exit. CE is, I don't know.
CE start.
Maybe it's yeah, it's something like that. I think maybe it's moving on to the customer end. Like any task someone. Sorry.
class testing. Yeah, no one
Class testing.
they were saying
Okay.
something.
I don't know. So this is the sequence, right? So we have that. So week by week, this is what is done, and then by the time we come to like about 4 weeks, we should have like basic packet processing by NAC, SNR, Ethernet package exchange with retimers, all that. So some of this is going to go on in parallel in Ericsson also, right? So sometime as soon as we bring ours, they are also in a rush. So our team members usually rush there, or there are parallel teams working in both places. But we usually leverage all the knowledge that we have gained by doing our own bring up. So fingers crossed, customer bring up should run much faster, right? So in Lionfish kind of things, I mean, usually in the traditional Intel board bring up, all that may take like 2-3 months, right? In the Lionfish case, I think on our side itself, the Linux prompt came up in like 2-3 days or something, and using that, we did it in Nokia in like 1 day or 2 day kind of thing. So that was, I mean, fantastic, right? So hopefully we'll do something similar here also. I think that was my last slide. Anyone has any question, comments?
Test away from it. So many small chips. Right?
Sure. Yeah.
You have to sort it or test it. What do you do?
Yeah, actually, wafer testing is like a totally different domain. I can't claim any kind of expertise on that, but that is actually more of, you have the complete wafer with the chips, but you are not checking anything related to chips at all. It's just like the characteristics of the wafer, is it good or bad at that level, right? The chip level, anything, even like leakage current, blah blah, all that comes after it's all broken down and put on the individual things. Okay, that was my last slide. That brings us to the end of the presentation. We are recording this session, and this will be posted on the Intel video portal. So you are welcome to send me any question, comments you may have individually, or post them on the Intel video portal as well, so others can benefit. Thank you all for attending the session today. Bye.